have certainly found that technological advances, they have provided, you can think of them as powerful metaphors for understanding the universe. What I have in mind is things like from mechanical devices inspiring the notion of the universe as a giant machine, to the advent of clocks and the notion of the clockwork universe that steadily ticks forward, steadily advances, to the advent of the steam engine, and then the notion of the universe as a thermodynamic system relentlessly degrading its initial order, to the advent more recently of computers suggesting a computational universe, and going further still with this metaphor, with the advent of AI, the notion that perhaps the universe itself is endowed with some flavor, some kind of intrinsic intelligence. Now, each technological leap has reshaped our conceptual framework for reality. And these metaphors, they not only reflect our current technological capabilities, but they also influence the direction of future scientific inquiry and philosophical thought. And one of the people who has been instrumental in advancing that most recent of metaphors coming from the computational revolution is our guest for this conversation. So I'm so pleased to introduce Stephen Wolfram, who is the founder and CEO of Wolfram Research and the creator of Mathematica, Wolfram Alpha, and the Wolfram language. He's the author of a number of books, and among other honors was named to the very first class of MacArthur Fellows. Stephen, so good to see you.
Likewise.
So I want to jump right in, and the basic theme of this conversation is, will AI somehow reshape the way we approach foundational scientific research? And just to get us going, what I did was I asked ChatGPT for a sample of human activities that it thought that it or other AI systems would take over. And the kinds of things that popped out are the things that you would imagine. Things like data entry, processing, customer service support, routine office tasks, things of that sort. Kind of long list that we see populating here on the screen. And then after this list was completed, as I often do with these systems, I say, is that all? Can't you come up with anything else? And of course it then does come up with more, and I'm not even going to bother, but they're the obvious things that would come to mind. But here's my point. Scientific research did not come out as one of the things that it thought that it would take over. And so are you of the same mindset that we will always be vital to that process? Or as someone who spent so much time revolutionizing how we do science from the computational standpoint, I mean, so much of what I've done I couldn't have done without tools that you invented. So where do you come down on the future of humans in scientific research?
I have to say, with respect to that list there, it's like not enough people have written that science will be informed.
That's
by
all
AI.
that it is, right?
Right.
Yes. Yes.
But in terms of what, will AI, for example, one of the questions is, in science, what does science try to do? Science tries to do things like predict what will happen. We say we know the equations, we know some rules for how a system operates. Can we just jump ahead and say, this is what the system is going to do? Now, we have reasons to think that that is fundamentally difficult. But there's this phenomenon I call computational irreducibility that actually I realize I invented that term 40 years and 4 days ago.
Is that right? I'm sorry we didn't have this talk 4 days ago. It would have been so clean.
Right. But this idea of computational irreducibility is, even though you might know the underlying rules by which a system operates, can you expect to kind of jump ahead and say, so this is what's going to happen, or do you have to follow those rules step by step as a computer would do it to see what's going to happen? So one question would be, can AI somehow magically do that jumping ahead that we seem unable to do? And the answer is no. I mean, it's as simple as that.
Yeah.
The ultimate answer is, it will not be able to break computational irreducibility because computational irreducibility it's irreducible.
It's its own limit, you're saying.
But so now the question is, are the things that we want to know things that are always part of that computationally irreducible process? Because even the very fact that science is possible is not trivial.
Exactly.
You know,
it could have been that we couldn't have gotten off the ground.
Right. There could be no sort of narrative that we can generate about how the universe works. It could just be the universe does what it does. It's all irreducibly doing these things.
You observe it, but that's all you can ever say about it.
Right, exactly. So the fact that we have laws of physics, scientific laws and so on, even that is non-trivial. And that is a consequence of the fact that there are always sort of pockets of reducibility within a computational.
Can we just unpack that key idea for a second? Because we have, for instance, some of those equations of physics. You know, somebody who is trained in physics knows what these mean. If you haven't been trained, these are the basic equations of electricity, and magnetism, Newton's law, Schrodinger's equation, Einstein's equation. All of these are kind of meant to do what you said. We put in the initial data, and then we don't have to follow the system step by step by step. This allows us to leap over those steps and get to the answer. Now, for somebody like me, that is the understanding of the universe that we have gotten. But you would potentially say that this is a little tiny weird pocket in which the physical systems admit this kind of a leapfrogging over the dynamical evolution, and that is not the norm.
Yeah, right. And I mean, sometimes, you know, in those very equations, like, for example, the one on the almost bottom right, the Einstein equations, right, is a case where there are lots of very complicated things that happen with the Einstein equations, black holes, all these kinds of things. And we know that in that case, we're kind of seeing through. We're seeing to things where we can't just say, we got the equations, we know what the answer is going to be. Some of those other equations are more of that character, where we got the equations, they give us a piece of firm reducibility, so to speak, where we can go find the answer.
But could it be that we're only interested in the reducible part of reality? Could it be that's all that matters?
Yes. But
all right, then. Thank you so much for this.
So the point is that's a very important point. It's an important point about the future of AI and humans and so on, that there is a lot that's out there. There's a lot that's possible. You know, if you just start inventing possible computational rules for things, whether they're part of the universe, not part of the universe, they do many different things. Lots of rich behavior, much of it computationally irreducible. The question then is, do we care about these things?
Right.
You know, we go essentially searching for algorithms. We find algorithms, but what are those algorithms for? Are they for things that we care about doing? Are they just algorithms that can run, but we're not connected to them?
Right.
And it's kind of so this is really the question: is what is the path of what we as humans care about?
Yeah.
And a lot of that is determined by things like what our senses happen to be. You know, we care about things that we can see. We don't care so much about things we can't see. A lot of the progress of science has been about realizing, whether it's a microscope, a telescope, an electronic amplifier, whatever else, about being able to detect things about the world that we didn't previously have access to. And then we started caring about it, and then we started making a science about it. So I think, you know, that's really the issue is how do we pick what we care about? So for example, let's say mathematics. You can generate an infinite number of theorems of mathematics. You can just go and systematically...
They're theorem generators that
absolutely. Right. And then the question is, out of that whole big meta-mathematical space of possibilities, where do we choose to colonize, so to speak? Where do we actually go? Where do we say, humans care about this part, we're going to live here, as opposed to just there's this vast mass of things we don't care about?
Do you have insight into that? I mean, in other words, there are theorems, I don't know, that have names, right? I mean, if they're named, then somebody cared about it at some point, right? And so is there a pattern among the theorems within the spectrum of all theorems that have been named or
I wonder. I mean, so I know in a few simple cases. So in the case of logic, there are 14 theorems that get given names in the textbooks of logic. And there is actually a principle about when they're given names. It's basically the simplest statement of something, of a new fact of logic ends up being given a name. So that's in that
sort of the root statement of a new tree of theorems that can be generated from
it. So the more general case, when you look at sort of all the metamathematical space and you look at kind of where are the theorems that have been given names, I've studied this kind of empirical metamathematics. It's a place where actually some kinds of AI, neural net kinds of things might be helpful. I haven't managed to get them to be helpful yet. But because one has to understand, what are the neural nets good for? And by the way, we should distinguish, when we're talking about AI,
yes.
we need to define what we mean by AI.
Absolutely.
Because in the time from 1956 when the term was invented to today, AI has meant many different things.
Yeah.
And many things I've done in my life, people said, when computers can do this, we'll know that they're smart and have true AI. And then when it's actually done, people say, well, that's just an algorithm.
Right.
That's not true intelligence, so to speak. So what's happened, there's kind of what can be done computationally, and that's a huge set of things that are very interesting and it's easy to be creative in the computational universe. You just pick at random some rule
and let it churn.
And let it run. And
yeah.
it'll produce some amazing pattern that's never been seen before. It's a piece of creativity, so to speak. Years ago, we even made a little thing called Wolfram Tones that made algorithmic music that way. People actually, the thing that really surprised me was that composers were telling me it was an interesting source of inspiration for something that I then developed. You would think a computer would be the thing that would kind of decorate something which came originally from human creativity, but no, it's the other way around. It's kind of like this was a seed that then the human can kind of make meaningful.
But that was not based on it studying a corpus of previous musical composition. That was a different kind of structure.
Right. That was a structure where it is just using the fact that in the computational universe you can have simple rules that produce ornate behavior.
Right.
But nevertheless, you can, as a human, you can kind of get some sense that there was something meaningful, there was some underlying rule to it. It wasn't just
so you could sort of feel that rule in some intuitive way,
yes,
underlying this more complex structure that emerged from it.
Right, I think so. But so it's very easy to be creative in the computational universe. The question is, are the things that you create things that humans care about? But the thing that's happened in recent times, neural nets were originally invented in 1943. And the neural nets that we have today that make our large language models and so on are really not that different from the neural nets that were originally suggested in 1943. What's happened is, well, it wasn't clear what was going to happen because, back in 1980 or so, I studied neural nets. I tried to get them to do things. I couldn't get them to do anything interesting. I was like, this is not going to go anywhere. I actually tried to simplify the idea of neural nets and ended up with these much simpler computational systems called cellular automata that I've studied for years. And that came from being frustrated that neural nets were too complicated.
Is that right? I didn't know that history.
Yeah.
I see.
Right. So at that time, one was trying to use simple neural nets, simple problems. Nothing worked. Then it got to, well, there was sort of really in 2011 was the time when things really took off, when these deep neural nets, many-layer neural nets, were successfully trained almost by mistake to do image recognition. It's kind of like nobody knew that having a more difficult problem and just bashing the neural net harder and harder, it would eventually learn.
Right.
This is a major scientific fact, actually, which we still don't understand. That is, you have a complicated neural net, you're asking it to solve a fairly complicated problem, and you just keep bashing it. You keep saying, here are the examples, here are the examples.
Just more and more data.
Right.
Yeah.
And more and more, and the fact that it manages to learn. It's not obvious what neural nets are potentially capable of learning. It was not obvious that when you bash them hard enough, they will successfully learn. But then the big sort of threshold was image recognition being done around 2011, and now, with large language models, we've got another big sort of threshold of being able to do something which we thought might require, quantum mechanics in the brain or something to generate fluent language, but it isn't true. We now know that we can just get a plain old neural net to generate sort of fluent human language.
How surprising do you find that fact?
I think it's a very interesting scientific fact. I couldn't have necessarily called it in either direction before the end of 2022. I don't think anybody could.
Yeah.
I think that it was, the people who worked on developing, for example, ChatGPT, they didn't know it was going to work. If they'd known it was going to work, they probably wouldn't have released it. But that's a separate issue. The fact is that it's a very interesting fact that language is basically simple enough that a thing that has the architecture of a neural net can do that. But
now, is that, do you think, because the neural net is at least inspired by the kinds of things that happen? And it's obviously not a direct representation of it. It's not a model of the brain. But the kind of processes are at least analogous at some level with things that happen in our head.
Absolutely.
Is that part of why human language, when filtered through these systems, was an efficacious way of trying to deal with them and analyze them?
Yeah, I mean, the fact is what neural nets do is the kinds of things that human brains do, and they do them presumably because their architecture is actually quite similar.
Yeah.
I mean, there are particular details of how brains work that neural nets don't capture. For years, my friends in neuroscience would say, oh, these artificial neural nets, they're nothing like brains. But as soon as the artificial neural nets manage to do really sophisticated things, now the flow has gone the other way.
Right.
What can we learn about neuroscience from what the artificial neural nets do?
Right.
I think the thing to understand is a lot of what neural nets do easily are things that we humans do easily. So for example, if you say, let's run this computational rule, 1 billion steps or something, a neural net doesn't do that. Nor do brains.
Right.
You know, if you'd say to a person, run this piece of mathematical code in your head, I can do something.
You could do it, but you're the only person on Earth that could do it.
I can't get very far.
Yeah, right.
It's there wouldn't be any bugs in programs if we could run programs in our heads.
Right.
It's the fact that we can't do that. We can't foresee what's going to happen. That means that we write code that might not do what we think it will do. But I think so we have to understand that what the neural nets do is stuff we find easy. Stuff we find hard, there's no reason that the neural nets will be able to do it. So for example, when it comes to science, there are plenty of things we find hard, and there's no reason to think the neural net can do it. If you say, this is a thing that a human could do immediately, then there's a reasonable chance a neural net could do it. If you look at the history of science, back before the late 1600s, science was natural physics, was natural philosophy, and people expected that you could just reason about how the world would work. There wasn't a kind of stack of abstract, formal kinds of things like mathematics.
Yeah.
It was just, we'll reason about it. Had we been at that stage in physics, now the neural nets would have been all over it.
You mean it would have been a neural net giving us Newton's law?
Yeah, I think so. I mean, I think but the fact is, by the time we're at this level of formalization that we have, where we're saying we're really, we've got these rules, we can run them, we can be very structured in what we do, this is not something that brains do well, and it's not something neural nets do well. And it's a practical, technological thing. The technology stack we built, it gets hooked up to large language models, and the large language model says, and now I'm going to call this tool to go do this computation.
Right.
And that's a thing, it's still trying to work out how to get that tool calling to work in the best possible way. But that, like for humans, it's like the human is not going to go and run the code in their head. They're going to run it on a computer. And it's the same kind of thing.
Now, I read this paper of yours, which I found really interesting, because it was the first one that I've seen, maybe there's a literature out there that I'm not aware of, that really began to look inside the large language model or the image recognition model to try to see what was happening inside the black box. I mean, most people say it's just too complicated. A human can't really understand the set of processes layer by layer by layer in this neural net and the updating, how does it, we can't really, but you gave a glimmer of understanding what's happening in there. Is there a way to summarize what you found?
Well, I mean, the big area that will emerge is LLM science, basically. The science of how, what LLMs are doing. Now, it's a bit like neuroscience. It's not obvious that there is a narrative science of neuroscience.
Yeah.
It's not obvious that, we go from the individual neuron firings to the words we say. The question is there an intermediate layer that we can explain, or is it just something that is a sort of computationally irreducible thing and then the neurons, collect together and eventually say this word? So that's the question of what is there that is computationally reducible that we can find in The large language model is very similar to neuroscience. I've done experiments where you do things that are just like neuroscience, where you just start zapping pieces of the large language model or whatever and see what does it do. So for example, a nice case of that is what happens if you take an image generation model and you say, okay, you tell it, I did one where I'm generating, picture of a cat in a party hat. Okay, so it produces, so how did it ever generate that picture? Well, it's seen billions of images from the web which have captions that say this is a cat, this is a dog, and so on. And it's able, what it's effectively doing is it's sort of generating an image from random noise, and it's going to something which it's set up to produce an image, some image, that is an image, a plausible image. And then it's got this kind of loop that's saying, is that image that I'm producing something that looks like a cat or not? But so inside that system, there's kind of a description of what it is producing that's an array of numbers. And you can say, a cat corresponds to a particular array of numbers, and a dog corresponds to another array of numbers. But you can go into the system at the level of that array of numbers and just start changing those numbers. You say, what do you get? Well, there's a place, numbers very close to the cat collection of numbers make a cat. Ones are close to a dog make a dog. The question is, what's in the interconcept space, so to speak? Those are two places in the space of images that can be generated, which are concepts for which we have names, cats and dogs. What's in between them? The answer is there's all kinds of stuff that we can see isn't just a random collection of pixels, but we don't have names for it. It's things that we have.
So like images that have structure, but not something that we've named in the past because they never cropped up or something. Right. And in fact, I think if we can bring it up for just a second, just to look, I think we have a few of those that we can show here. This is number 44. Are these examples of those kinds?
Those are good interconcept images.
And so is this part of the answer, or at least the glimmer of considerations when you say, what is it that we find interesting?
Sure.
So somehow it's more interesting than noise, without any doubt.
Right, well, so one day, one of those pictures may correspond to a style of art that somebody calls, purple cubic art or something.
Right.
And then everybody will know about it. I mean, you can see this happening, like fractals, for example, nested patterns and so on. That was an idea that people hadn't really had seriously until the 1970s and 1980s. But nevertheless, there were mosaic layers who had produced those patterns in the 1200s. And if you look at what did the art historians say about these lovely mosaics that contained these nested patterns, they ignored the nested patterns. They talked about the lions and so on that were portrayed in the mosaics, but they didn't mention the nested patterns. Today, people who are writing about those mosaic layers, they'll all be all about nested patterns and so on. So it's a question of what do we, it's kind of a somewhat social construct of what do we kind of identify as a concept we care about, give it a word in our language, and so on. This sort of relates to this question about what will the AIs eventually do. I mean, people say, will the AIs sort of take over everything? Well, the AIs can go out and explore this computational universe, and they can come up with all kinds of interesting interconcept kinds of things. But the question of whether that can happen as a kind of the society of AIs can consist of a lot of these complicated things going on, then the question is, how do we humans relate to that?
Yeah.
It's a little bit like how we relate to the natural world. I mean, the natural world is doing all the kinds of things it does, and we find these places where we intersect with the natural world, can make use of the natural world for human purposes and so on. Sometimes the natural world does bad things that we don't like it to do, all those kinds of things. I think that's the same kind of way to think about sort of the future of what will happen with the kind of the society of the AIs. And this question, for example, for science, the AIs can go exploring all sorts of directions kind of in the computational universe of possibilities. Some of those will be things where we say, that's really exciting technologically, we really care about it, it's really something that relates to something we're interested in, and some of it will just be, it's out there, it's not clear what its significance is.
And do you foresee then a time, and maybe that time is right now, where maybe the role of AI will be to find these interconcept space domains, draw our attention to them, and then perhaps we begin to see whether that's the new direction of science that we find fruitful to follow?
Right, so the interesting question there, I think, is whether the AIs can learn enough about us, can model us
To
well
tell
enough.
us what to look at?
Yeah, right, which is a very similar problem to, for example, we're building an AI tutor system.
Yes.
It's actually the main thing about AI tutor systems is they're very hard to build. That's the main thing to know about them. It's very easy to make a demo. It's very hard to make something that will actually work. But one feature of making that actually work is that you essentially have to model what the student understands. Because in a perfect world, what would happen is, you've got your AI tutor assistant type system, and it knows what you know.
And it knows you so well that it knows how to teach you what you need to learn.
Right. It says, this is the one thing you need to know, and then it'll unlock this whole direction.
Yeah.
And so that's the kind of thing one is potentially, that knowing us, knowing about us is kind of part of the story. I mean, I think the thing to realize about AI and kind of what's happening with sort of the automation that AI makes possible, a lot of it is shining just a brighter and brighter light on what we want to do, what we are like, what we think should be done, these kinds of things.
Now, along those lines, though, I mean, going back to the case of large language models, doing what they do in an impressive way, in part because their structure is resonant with our structure, and language is something that we do reasonably well. Science is not something that our species does reasonably well. It's like a few outliers in the grand population. And if we go further to those who've made a contribution that really mattered, it's, relatively speaking, a handful of members across the human species that have done that. So would that suggest that AI modeled on us is the wrong way of going about it, and there may be a different structure where science is, it's like language to me. Everybody can do it, and something of that sort.
So I think it's an interesting question, whether an AI, neural net-based AI, can do well things we can do well. There are things that are purely scientific, like let's take the three-body problem, Earth, Moon, Sun, gravity, all these kinds of things. That's something where you might imagine that an AI, when shown a bunch of examples of the three-body problem,
just figure it out.
Would just figure it out.
Yeah.
And but I think, and it's not obvious. We don't know. Are there pockets of computational reducibility within the three-body problem that we've never noticed? That the AI might be able to notice? It's possible.
So we have, actually from your paper, so as far as the three-body problem, can you give us a sense of, first of all, you should probably say what the three-body problem is.
So I mean, the three-body problem. So one of the things that Newton was big on was figuring out the law of gravity and figuring out if you have an idealized star and a planet is going around it, he figured out that it goes in an ellipse. You can prove that mathematically it goes in an ellipse. Okay, now what about if you have three bodies instead of two? Like, for example, Earth and Moon and Sun. Well, then it's much harder. And in fact, Newton, one of the things he says in his Principia book is he has a statement, these methods will allow us to predict the motion of the moon. Then he proceeds to do it, and the end of the chapter is, I think it's, but the apse of the moon is twice as swift. In other words, he got the wrong answer by a factor of 2. This is interesting in the history of science, because you might have said, it was experimentally proved to be wrong, therefore the whole theory falls apart.
Right.
But no, that wouldn't be the right conclusion. I mean, so the three-body problem is hard. And because the motion of bodies...
Each body pulls on the other and is complicated
and you
network.
Get pictures like this showing...
And so the three colors here are the motions of the three bodies?
Yes. And so this is like I think the one on the bottom right there, two of the bodies are just going off
orbiting.
Like a two-body system. And orbiting each other.
And one's getting flung out or something, the green one.
Right. And so, these are just random examples of the three-body problem. And the question is, can you figure out, okay, AI, what's going to happen in each of these cases?
And so you give it a huge number of examples that are correct. And say, find the pattern. Now give it 3 other masses with presumably some initial velocities and say, go at it, tell me what the trajectories will look like.
And it doesn't do very well. At least,
and we wouldn't do very well either. So
we do horribly.
Yes,
and it does about. I don't know whether I haven't tried to do this by hand, so I don't know how it does compared to us. But it doesn't do very well.
Right.
It'll say there's going to be a squiggle. but it doesn't say what what's going to happen in the squiggle.
Right.
Now, is that a limitation? Is that an engineering limitation of our current AIs? Or is that something that is fundamental?
Well, that's the question. I mean, do you have a sense on that?
Well, ultimately, this is a computationally irreducible problem. So ultimately, you will not be able to answer the whole thing.
You've got to crank through it.
Right. Are there special cases that could be answered? Are there
highly
bigger,
symmetric?
Right.
Yeah.
Right. So I mean, there are some which we can plainly see this is going to be easy. There's some where it looks like a big mess to us. Are the ones which it looks like a mess to us, will the AI say, no, actually, I can notice that there's this build pattern there, which will tell me what's going to happen.
Yeah.
So I can't say that won't happen. I think it's an interesting question whether these sort of slices of reducibility are things, we've found a bunch of slices of reducibility to lead our lives with.
And that's what we call science.
Indeed, absolutely.
Yeah.
So then the question is, are there other slices, you were alluding to this earlier, I mean, are there other slices that are fundamentally different from the ones we've already found that are findable? And will they be findable by a neural net like AI?
Yeah.
We don't know the answer to this.
Right. But that would be astounding, right? If we were, our attention is drawn to something and there's this whole other universe of things that we just never even considered or thought of.
I think one of the things to think about there is part of the way we view the laws we come up with in science depend on the senses that we have to look at the world. And one thing that's interesting about AI is their natural senses might be very different from ours. That is, you've got this AI and it's connected to all these sensors, that are IoT sensors put all over the world and so on. And that's not what we experience. We experience, well, we're looking with our eyes at some, maybe a screen, but we're looking at things like that. Now, what it will see, what it will sort of get a sense of, may be something very human incomprehensible. I mean, it's kind of like even if we look at a whale or something, which probably has all kinds of sensing of fluid motion
that we just don't know
familiar with. Yeah. Right. And if you could talk to the whale and it would tell you, oh, I know there's this law of physics that is this weird hydrodynamic thing that we look at it and say, okay, that's amusing, but
the way most people look at us when we talk about things that are of interest to us. But
yes, in the physics world.
Yes, exactly. And so. There therefore is a significant chance that even if an AI system properly configured could find something interesting in the sense of this other realm of structure that we've never thought, we may simply be insensitive to it and think it's nothing.
Exactly. Right. I mean, I think this is what you see kind of in the computational universe all the time, is you see these very complicated patterns. I probably maybe got some examples of those, but that get generated, and it's like, what does this mean? Is this significant?
Yeah.
It's you have to build this whole kind of tower of human experience and thinking and so on to decide that it's significant.
Yeah.
And I think the case that's sort of an intersection is where that there's some objective you want to achieve, and maybe there's a way to get to that objective.
Oh, I see. If it gets to the answer, then you're certainly going to take seriously whatever path it took to get there.
Right. So one question is, how does machine learning, how do neural nets and things get to an answer?
Yeah.
Actually, I just did this thing a few weeks ago. So this is an example. The question is, this is kind of a very microscopic toy organism. So the thing on the left is kind of like the genome for the organism, the rules for the organism, and the thing on the right is kind of the behavior of the organism when it starts off from some little seed. So this is what happens when you say, I'm going to change the rules of the organism. I'm going to change the genome of the organism. I'm going to mutate it.
Yep.
I'm going to pick those mutations that make the thing live longer. And what you see, which I find pretty interesting, is it manages to live a long time, but it does it in an incredibly bizarre way. It's like you wouldn't have, if you'd been engineering this is not what you would have built. You would have built something that kind of moves systematically back and forth a certain number of steps. Each one of these is based on some set of underlying rules.
Yep.
You can think of it as the genome that is producing this organism, so to speak. And what's happening is, at every step, you are saying, I'm going to make a mutation to this set of underlying rules.
Yep.
You may make a whole bunch of mutations, thousands of mutations, most of which are total failures.
Okay.
But eventually you'll get to a mutation that manages to get the pattern to live longer.
I see. And the length of duration is the
fitness in this particular case.
Yeah.
And so what this is showing is how the thing essentially adapts to be able to live longer. And what you see, the important thing, maybe there's one more slide, I think, in this sequence. So those are 3 examples of sort of how the evolution works.
Yep.
And what you see is they're all different, and they're all kind of bizarre, and you kind of see the thing progressively building on what it already figured out. It's kind of like you think about the fossil record. At first, there were organisms that had a few legs, and then there were organisms that had more elaborate jointed legs and so on. And that's kind of what you're seeing here. And so it is achieving some objective, in this case, a rather simple to describe objective, but in a very complicated way. And what I think is relevant about this to things like neural nets and so on is when they learn something, the question is, how did they learn that? What's inside? And is it something where we can, for example, you were asking about sort of the LLM science, the narrative science of what's going on. Is it something about which we can explain? Like in this case, you say, why does it live a long time? Well, you look at the picture, you can see it lives a long time.
Right.
But if you start saying, what is the mechanism by which it lives a long time?
Actually looking at the dynamics and trying to get some feel or rule or rationale or something.
Some narrative about why it lives a long time.
Coherent story of how this thing. Yeah.
It's pretty difficult with these.
Yeah.
And that's kind of a model for what's happening, I think, in neural nets. It's been very difficult to kind of grind down what's happening in neural nets to the point where you can even make pictures like this.
Yeah.
But my guess is, something I happen to be looking at right now, is, so I don't have the answer yet, is kind of what, when you look inside a neural net, what was the structure that it built to be able to know that the next word should have been, this or something? What I'm guessing is that it does it in this way that is not readily explainable.
Yeah.
So and then the question is, but that's a case where the output happens to have a narrative description, but the mechanism inside does not.
Does not. So one final arena in the last couple minutes, because we're unfortunately running out of time, because I could keep this conversation going for quite some time, but we do have limits here. AI systems that can improve themselves, recursively self-improving systems, is that an arena where you see that there could be a radical new kind of AI system emerging?
I don't know. I think, the worst thing that can happen is that most of the content of the web that's used for training data and so on ends up being AI generated. And then the whole thing kind of reverts on itself.
Right, exactly.
And it reverts to kind of the lowest common denominator of everything. So, I mean, it is a thing that, modern AI systems, I don't know, your average self-driving car, for example, it got a bunch of data from actually looking at what really happens.
Yeah.
And then it's basically running video games to generate more synthetic data that it can train on. Now, I actually think it's in a sense, that's a sign of probably that neural nets aren't quite the right way to do this. Because in a sense, you're saying, we've got, even in some cases, you're saying, I'm going to synthesize, I'm going to take equations that allow us to compute what happens, and I'm going to run these a bunch of times to train a neural net that's going to tell me what happens in these equations. But you could just run the equations to find out what's going on. So I think, one of the things that is, one of the things that will happen with neural nets and so on is, right now, the only way we know how to train neural nets is by this give examples, train them, and so on. It's very, and they can call tools, but that's a very it's not a fine-grained process. It's kind of like you do a bunch of LLMery, then you call our computational tools or something, and you go back to the LLM. In the future, that will be a much more fine-grained thing. I mean, the fact that an LLM has been trained to the point where it knows the 3rd decimal digit of the population of New York, it doesn't need to know that. It needs to know New York is a big city, but it doesn't. The fact that that's been, woven into what the neural net has been trained on is not really the right thing, and that will be sort of taken apart. And so when you talk about kind of the neural net learning, I think the thing that we're learning is that the neural nets are showing us that there are actually scientific-like laws that we didn't know about,
right.
like laws about language. Like, one of the things about language is we've known forever that there's a kind of syntactic grammar of language. We have, in English, it's noun, verb, noun. But there are many noun, verb, noun sentences that are absolutely meaningless.
Yep.
But what I think we're learning is that there's a construction kit of meaningful sentences, which is kind of a semantic grammar, and that's a kind of a law of science, so to speak. And we can use that to get much further. So I'm kind of, the idea that we feed the neural net back the thing that it knows itself, there is a certain amount of optimization that can be done that way.
But it's not,
my guess is
yeah.
that what you're ending up with is kind of like it's spiraling into this point that is the kind of the thing you get by having a neural net eat its own tail, so to speak.
Yep.
And I doubt that that's a terribly interesting point. I mean, my guess is that it gets more and more banal, basically,
right.
as it feeds back on its own content. I mean, there are many things we don't yet know. I mean, another thing that's of considerable interest, I think, is when you think about a whole sort of society of AIs, how will it behave? What will happen in AIs? The LLMs
interacting with AIs and...
Yeah, right.
Yeah.
I mean, they're a pretty good proxy for humans
yeah.
in many ways. What will happen when you put a billion of them together? And how will that evolve like human societies have evolved? What will be its sort of, what will be the emergent ethics of those systems, all those kinds of things.
Yeah. So a final question I've asked to a number of people who have been sitting in that chair for these conversations. How do you think about science, creativity, AI? I mean, is the human input and what we like to think is some kind of special quality that we bring to this endeavor, will that always be essential to scientific progress, or will that be usurped by one of these AI systems?
Depends who the consumers are. If the consumers are humans, it matters what the humans think we should do.
Yeah.
I mean, if you're saying what's out there in the computational universe for the AIs to find, then
they'll just find it.
They'll just find it, and it's
okay.
not. I mean, so in other words, this question, it's like people say, well, what can be automated? One of the things you can't automate is to know what you should be trying to do, because that's there's an infinite set of things you could be trying to do. We get to choose particular things we want to do, and it also relates to kind of what will the jobs for humans be? And the typical thing that you see in the history of automation is that a thing that became quite mechanical got automated. That opened up a bunch of new possibilities.
Yeah.
And a lot of those new jobs had to do with people making choices about what should happen. And that was the job, was to make those choices.
Right.
And I think the same thing, we're going to see the same thing.
So that will be the role that we will always have as long as we are here.
Right.
So thank you so much. Fascinating conversation.
Thanks.
Thank you very much.